Thank you very much for being at this presentation. My name is Mohammad Khajavian, and today we're going to explore the application of machine learning in chemical engineering and how we can use the machine learning in the chemical engineering. The title of the presentation is Unlocking the Power of Machine Learning in Chemical Engineering. Why this matters? Chemical engineering is the foundational to numerous industries: pharmaceuticals, energy, materials, water treatment, and more. Traditional processes are sufficient, but they have limitations, especially in handling complex and nonlinear processes. Machine learning offers new tools to optimize, predict, and even innovate within these spaces. First of all, we need to have a very specific definition of machine learning to understand the whole definition of machine learning and its application in chemical engineering. Definition of machine learning here is machine learning is a subset of artificial intelligence, or AI, that involves training algorithms to make predictions or decisions without being explicitly programmed. In these definitions, we need to understand two words: artificial intelligence, and without being explicitly programmed to understand the whole definition of machine learning. So in the next two slides, I'll explain to you what is the meaning of artificial intelligence and what is the meaning of without being explicitly programmed. How artificial intelligence works? In the artificial intelligence process, we have a definition that says that artificial intelligence is the simulation of human intelligence using computers. This process includes three important processes containing learning, reasoning, and self-correction. In the learning process, we put our data into the system, and systems start to learn. But in the reasoning process, systems start to find a pattern in the input data. Let's imagine that we have a reactor, and when we increase the temperature, we can increase the product. And it's a kind of pattern. And in the reasoning process, artificial intelligence like to find this pattern that when we increase the temperature, or for example, when we decrease the pressure, we can increase the product, and it's a pattern. And finally, systems start to self-correct itself. At the end of the reasoning process, systems start to compare its prediction according to the input. If they were close, system end to the output, but if they weren't close, the prediction and input, system start to self-correct itself, which is one of the most important parts of artificial intelligence. The other word in the machine learning that that make a difference between machine learning and other artificial intelligence processes is that in the machine learning we don't need explicit program. In the explicit program, human needs to write very detailed instruction for computer to follow. But in the process without machine learning, we need to provide very specific instruction for the computer to follow. But in the machine learning, we put all of raw data into the system, and system start to learning, reasoning, and self-correction. So two kinds of important words in the definition of machine learning. First, artificial intelligence, including learning, reasoning, and self-correction. That self-correction is the most important part. And then we have without explicit program, or without needing very specific instruction for computer to follow. This is very comprehensive chart of machine learning. We can divide machine learning into the supervised and unsupervised learning. And in the supervised learning, we have two kinds of process: classification and regression. And all of these can be divided in two sections. For example, in the regression, we have linear regression, ensemble methods, decision tree, neural network. We have neural network in two processes. And because classification and regression are being used very in a variety of chemical engineering processes, so we focus on these two words. So in the next 4 slides, I'll explain supervised, unsupervised, and classification and regression to understand a part of this process that that are being used very well and in a wide processes of machine learning, of chemical engineering. In the supervised learning, we have labeling process. To simplify, I have example here. Let's imagine that we have an input data that we want to recognize the elephant, camel, and cow from each other. And in this process, in the supervised process, we label our input data according to our output. In other words, we are using our output in the input raw data. How? In the input data, we help our system. We say that when you are seeing an animal which is big and black, call it elephant, and in this input data, and when you are seeing an animal in this input data which is brown, call it camel, and when you are seeing an animal which is black and white, call it cow. And as you can see, all of these labels we have in the output, and this is a kind of supervised learning. In the unsupervised learning, we don't have this kind of labeling. We put all of raw data into the system, and system start to learning, reasoning, and self-correction. Supervised learning can be divided into the two sections, regression and classification. In the regression, we have just numeric data, and in the classification, we have two kinds of data. It can be both numeric, but also we need categorical data. What is the meaning of categorical data? In this example, we have more classification on regression and classification. Let's we want to predict house prices using regression and classification. In the regression, we have the input that says that when we have a house with a 1,500 square feet, 3 bedrooms, and 10 years old, the output is $40,000, and in the classification also we are saying we're having the same input that the house with 1,005 square feet, 3 bedrooms, and 10 years old. The output here is single family. The difference between regression and classification here is single family, or output is a category, and here $40,000. The output in the regression is the continuous value, but in the classification it's a category or class. Here we can say double family, or a family with 3 children, more than 3 children, or less than 3 children. That's a category, it's not about number. Then the application of machine learning in the world, in different science, manufacturing, healthcare, e-commerce, automobile, insurance, and transportation. But as you can see, it's a very wide application, and we need to narrow it down to the most important application of machine learning, especially in chemical engineering. In this slide, we narrow it down to the application of machine learning in chemical engineering: quality control, fault detection, product formulation, data-driven research and development, process optimization, material discovery, molecular modeling, process simulation and modeling, and finally environmental impact and sustainability. Here I have 6 examples of the application of machine learning, and or the applications that we can tackle in the chemical engineering. Let's imagine that we have a quality control process and we have a production line, and at the end of the production line we want to qualify our product, and we can put machine learning at the end of this production line to recognize for us whether the process or whether the product that we are producing is well enough to enter the market or not. If it was okay or good, system allowed to enter into the market. If not, system return it to the first or initial points of production line. Fault detection, let's imagine that we have a factory and there is a possibility of explosion. Machine learning can predict that possibility and prevent any kind of explosion in our system. In the process optimization, for instance, we have a system that we want to maximize our product or we want to minimize our waste. Machine learning can recognize these points and maximize our product and minimize our waste. Product formulation, when we have A and B as a raw material, that's okay, but when we have A, B, C, D, E, F, G, H as a raw material to produce product, new product and novel product, it's very difficult to find a ratio between raw material to produce that product, but machine learning can perform this task very easily for us. For the data-driven research, let's imagine that we have a factory here in Malaysia and we want to maximize our product. It's very time-consuming and we need to put a lot of money, and it's very costly for us to gather our data to maximize our product. We need a lot of experiment in the R&D section. But when we have the data for the same product in other countries, it doesn't matter what that this country, but the same product, we can use those data and put it into the machine learning and optimize or maximize our product. In the environmental impact, machine learning can predict a pollution in the environment and find a solution before it happens or prevent it in this way we can prepare ourselves for that pollution in the future. But in all of those processes that I explained in the last and previous slide, we need modeling and optimization. Why modeling and optimization are indispensable in chemical engineering? It's an exact definition because modeling and optimization allow engineers to simulate complex systems and understand their behavior and improve and enhance their performance. These tools help in designing processes that are more efficient and more cost-effective and also environmentally friendly. So here we want to talk about the application of modeling and optimization in the chemical, in the machine learning, and also integrate that in the machine learning and chemical engineering. Stages for modeling and optimization of a process. First, we need to define our objective. For example, we want to maximize our product or minimize our waste. Then we need to model our process. Then we need to analyze our model, whether the model that we are producing is working well enough or not. Then we need to implement our optimization method. And after modeling, we have optimization, and then validating and evaluating the whole process to understand whether the whole process is working well enough or not. But what is modeling? Modeling is the process of creating a representation of a system, object, or concept, usually to understand, analyze, or predict its behavior. Here we have an example for modeling the fuel efficiency of a car. The objective here is to predict the fuel efficiency, let's call it MPG, and for every modeling process that we want to talk about, we need independent parameters, the parameters that we can change. And also we need dependent parameters, the parameters that can change according to the independent parameters. Here, weight of car, engine size, and horsepower, or independent parameters, are the parameters that we can change in the factory. But MPG is our target, or is our Y. When we build our model, here we have x1, x2, x3 as in one side of our model, and in the other side we have our target, and D is our interception. This is a very simple process of modeling. For example, we are saying that when we increase the weight of the car, we can increase the MPG, or according to this model. But the other process after modeling is optimization. In the optimization, machine learning can optimize our process better because of self-correction process. And let's imagine that we have a reactor, and when we increase the temperature from 100 to 200, we can increase the yield of product, but from 200 to 250, it is stable, and we don't have any change in the yield of product, and then it decreases. It is more possible that machine learning processes can recognize the 200 as the optimal temperature, and non-machine learning can recognize 250. It is true that we have the same yield of product for machine learning and non-machine learning, but 200 is less temperature, has less temperature, and that means that less temperature means less energy consumption, and less energy consumption means more efficiency for our system. So machine learning, because of the self-correction process, can come back to the 200 and recognize it, but non-machine learning cannot come back to the last point and recognize the optimal temperature. What are the main differences between machine learning modeling and classical modeling? In the machine learning modeling, algorithm learns from data without explicit program, but classical modeling involves more manual steps. We need to write a lot of code lines. Less flexible for classical modeling, and high flexible, and it can handle, as I said before, nonlinear relationships and high dimensional data. And finally, machine learning is capable of adapting and evolving as new data arrives, but classical modeling don't have this kind of feature. What it means, what's the meaning of capable of adapting as new data arrives? Let's imagine that we model our process using machine learning and non-machine learning, and right now we want to put new data into the system. And when we put new data into the system, machine learning modeling can perform better than classical modeling or non-machine learning modeling, and also this is one of the most important powerness of machine learning in predicting our data. Steps in the machine learning modeling: problem statement, data collection. We need to collect our data, set our boundaries, data pre-processing, for example, normalizing our data. We need to splitting our data, then select our algorithm, train our algorithm, evaluate our algorithm. If it was okay, we go for the last point, output. If it wasn't, the system come back to select the other algorithm. Right now, we have different types of machine learning modeling methods. Which one of these we can use for different processes in chemical engineering? different types of data for model selection. We have structured data and unstructured data. Very simple, structured data can be displayed in rows and columns, and unstructured data cannot be displayed in rows and columns, for example, in the data in the Excel file or in the data frame. And here, for the structured data, we have numbers, dates, and for the unstructured data, we have image and audios, videos as input. So according to this selection, we can use different types of machine learning models. We have, these are just a few of machine learning models: artificial neural network, random forest, decision tree, and linear regression, and every one of these work based on different approaches. But how we can recognize that whether we are able to use a structured data or unstructured data in one of these machine learning models? As a rough estimation, for example, we say that when we have a structured data or numbers, it's better to use decision tree, random forest, and linear regression. And when we have unstructured data or audios, videos, we can use artificial neural network. Also, we can use structured data or numbers as the input in this machine learning based modeling. What software we can use for machine learning modeling? My suggestion is Python. Also, this is a statistical result for the evaluation of using different software in machine learning. Python is very, very popular for using in machine learning. And so my recommendation is Python, especially the Colab environment, which is the online and free environment for writing codes in the Python. Python is scalable. That means we can convert our codes into the software, and when we do this, in the future, developers as software engineers can use our software or machine learning modeling to develop them, and it's very, very professional for converting our coding into the software. Multi-purpose language, we can use, we can connect Python to the different software, and then we can use it in different environments. And for the person who is a beginner in machine learning, it's very useful because we have different database, different tutorial to learn, and very resources to learn machine learning. Here is an example for the application of machine learning in the optimization of batch absorption process. In the very brief explanation of the absorption process, in the absorption process we have pollution, red points, and we want to absorb our pollution using adsorbent, green parts, and here we absorb these red parts and clean water. This is the absorption process of pollution in the water. This is data frame related to the previous slide. Let's imagine in that container we can set our adsorbent mass on the 0.08 and initial concentration of 150 and pH of 4.5, and we conduct our experiment and we reach to the target or Y or removal of the pollution, which is 57. This is the first data point, and here we have 21 data points. When we collect our data, these are independent parameters, x1, x2, x3, and y is our dependent parameters. And when we collect all of this data, we can go for machine learning modeling, and in the real and practical process, we did that, and we perform our modeling using non-machine learning and machine learning processes, and at the end we reach to the R square of 0.42 and R square of 0.93 for CCD, or central composite design, or non-machine learning model, and random forest respectively. And as you can see, this distribution of points in the machine learning modeling is much narrower than here. So according to the result, random forest or machine learning is performing much better than non-machine learning, and so we can reach to the result that machine learning is predicting well the absorption process than non-machine learning process. And after modeling the process, then we have optimization process. In the optimization process, we optimize our process using machine learning and non-machine learning processes. And in the non-machine learning, the calculations was the pH of 6, initial concentration of 49, and absorbent mass of 0.012, that when we perform this calculation, the calculate removal was 86, and when we come back to the experimental section to reconduct our experiment, we reach to the 71% for the experimental removal. And for the machine learning or random forest, calculated the pH of 7, initial concentration of 59, and absorbent mass of 0.020 as an optimized point for maximizing our removal, and the calculated removal here is 98%. And when we come back to the experimental section and reconduct and we perform our process and this optimized process, we reach to the experimental removal of 96%. So because here for the non-machine learning, the distance between 71 and 86 is far, it's not predicting very well. But in the machine learning, because the distance between 98 and 96% is close, so we can reach a conclusion that random forest can perform much better than non-machine learning. Thank you very much for listening to this presentation. These are the contact information of my supervisor, Dr. Suzy, and also me, that I'll be happy to answer any question that you have after this presentation by this contact information. Thank you very much.